Television camera is positioned 4,000 feet from the base of a rocket launching pad. The rocket rises vertically and its speed is 600 feet per second. At the instant it has risen 3,000 feet. We have two parts to this problem. Part A is how fast is the distance from the camera to the rocket changing at that moment when the rocket has risen 3,000 feet. And part B, if the camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing at that same moment? Okay, so to get a kind of an idea of what's going on here, let's make a sketch of what's happening at arbitrary time t. Let me get my pencil here. That should do it. Okay, here we go. Okay, here's our sketch of what's happening, not at a particular time, but at arbitrary time t. There will always be a right triangle formed. Here is the camera right here at point C. Here is the rocket at arbitrary time t. Okay, so at that arbitrary time t, the rocket is at a certain height. Let's call that height x. And that x is a function of t. Okay, and of course the rocket is rising, so that x of t is changing constantly. And the distance from the camera to the rocket, let's call that z. That's also changing. It's a function of t. Okay, so call it z of t. And here's the angle of elevation of the camera. Let's call that angle theta. It's a function of t, so we'll call it theta of t. Okay, and then this distance here is our 4,000 feet that we were given in the beginning of the problem. Okay, so that's 4,000 feet there. That's not changing. Okay, so in part A, we want to figure out how this x of t is changing at the instant when x of t is 3,000. Okay, and we've got this picture of what's going on. We've got all our changing quantities of t here, and we also know a little bit about what's going on here. We know that the speed of the rocket is 600 feet per second when it is 3,000 feet high. Well, that 600 feet per second, that's the derivative of x with respect to t at the instant when the rocket is 3,000 feet high. So let's write down that we know that. We know that dx dt when x is 3,000 is equal to 600 feet per second. Okay, so let's say it's 600, and let's just remember that it's feet per second. Okay, so that's known. Okay, let's go ahead and get into part A here. What we want in part A, fix that X there. What we want in part A is the rate at which z is changing with time at the instant when x is 3,000. Okay, so we want to find dz dt, or z prime of t, when x is 3,000. Well, in order to do that, we need an equation that has z prime in it, so we can solve for z prime and we'll have z prime. Well, we can't just jump right into that equation. We first have to get an equation that relates the z and the x, and of course the 4,000, and that will come from the Pythagorean theorem. So let's write that down. We have z squared. This is just the Pythagorean theorem. That's equal to x squared plus 4,000 squared. Okay, so that's the equation that relates the changing quantities. Okay, now we'll use implicit differentiation to get an equation that relates the rates, that has the rates in it. So we'll take the derivative of this equation, both sides of this equation, with respect to t, of course using the chain rule. On the left side, when we do that, we get 2z let me write dz dt as z prime. So we get 2z z prime. That's going to be equal to, on the right side, we get 2x x prime. Okay, now we want z prime, so let's go ahead and solve for it. And we get that z prime is x times x prime over z. Okay, and we want this z prime when x is 3000. Okay, so let's specify that we're going to put the x equals 3000 in. In fact, we're going to put in everything we know is going on when x is 3000. And we'll get the z prime at that time when we do that. So z prime is equal to, x is 3000, so we have our 3000. Now remember, this is what's happening at the time when the rocket is 3,000 feet high. So yeah, the x is 3,000, but the x prime is 600 feet per second. Okay, then we need to divide by the z, but remember, this is happening when x is 3,000. So if we come up here to our triangle, we've got 3,000 here, 4,000 here, so we've got a 3, 4, 5 right triangle. That means z is 5,000. So all we have to do now is simplify this and then put the units in. We can cancel our thousands here, so we have 3/5 times 600, and then 5 goes into 600 120 times, so we get 3 times 120, so numerically speaking we have 360. Okay, let's see what our units are. This is z prime, so it's dz dt, so it's z units over t units. Okay, and z is in feet and t is in seconds, so this is 360 feet per second. Okay, and that's the answer to part A of the problem. Okay, let's go ahead and do part B. Now, part B, we do the same thing, except we need theta prime instead of z prime. So we need our equation relating our changing quantities to involve theta. And of course, that means we'll use trigonometry. If we look at our triangle here, we see that the tangent of theta at time t is equal to x over 4,000. Okay, so that's our equation that relates theta and x. Let's go ahead and use our implicit differentiation, take the derivative of each side with respect to t to get the equation that relates the rates. So the derivative of the left side is secant squared of theta times theta prime and it's going to be equal to the derivative of the right side, but that's just x prime over 4,000. Okay, now we want theta prime, so let's go ahead and solve for it. When we do that, we get theta prime is x prime times secant squared of theta. Actually, it's divided by secant squared theta. Over 4,000. Okay, so let's just change that to a cosine squared theta there. Okay, and that'll take care of the fact that what we really did from here to here is multiply both sides by cosine squared theta. Okay, now what we have to do is put in all our numerical values and we'll have our theta prime. Of course, get the units right as well. Okay, so theta prime is our x prime, which we know is 600. And then we need times cosine squared of theta, but again, remember this is happening when x is 3,000 and z is 5,000, so that means the cosine of theta is 4,000 over 5,000, which is 4/5. So we've got 6,000 times 4/5 squared, and then divided by 4,000. Then we simplify this, so we can cancel the thousands here. So, and then we'll have a 6 over 4 when we do that, but that's 3 over 2, so we'll have a 3 in the top. Okay, and then from the 4/5 squared, we get a 4 squared, which is 16. And we get a 5 squared in the denominator, and we still have a 2 down there from the 6/4. So the denominator, we have 2 times 5 squared, which is 2 times 25. And let's see, that's 24 over 25. And the units, see, this is d theta dt, so it'll be theta units over t units, so that's radians per second. And that is the answer to part B. Thanks for watching. Okay, I need to fix a mistake. This x prime right here should of course been 600 instead of 6,000. So let me get rid of that 0 there, and that's of course like dividing this by 10. So I can just put a 10 over here. Okay, and it's going to be dividing this by 10. That's kind of weird looking, but the correct answer will now be 2.4 divided by 25. And of course, you can put that in a different form if you want, a nicer form.